This is the story of magnetic forces, or what happens to a moving electric charge when it encounters a magnetic field. So the setup is as follows. I have an object that is carrying some kind of net charge Q because it either has an excess or deficiency of electrons, and it's moving with some velocity v, that is to say with some speed v in some specified direction, and then it encounters some kind of magnetic field that is set up by some other entities. And the question that we want to ask is what kind of interaction is going to result from the motion of the electric charge in this magnetic field. Turns out one way you can think about that is in terms of forces. So you can think about the magnetic force that a charge moving with some velocity in a magnetic field experiences, and that would be given by this expression, which is the net charge times the cross product between the velocity vector and the magnetic field vector. This is one of the expressions that are easy to remember because it kind of reads itself. This is the magnetic force on a charge moving with some velocity in some magnetic field. Now, obviously, I can think about this in terms of the cross product, the way we do it in any kind of coordinate system, whether it's a Cartesian one, so you do the I hat, J hat, K hat, etc., or you could calculate the magnitude and the direction separately. So in this case, for example, the magnitude, if I want to calculate the magnitude separately, then the magnitude of the force would be equal to the magnitude of the net charge times the magnitude of the vector that results from the cross product of V cross B. And you know that this one way to calculate the magnitude of that resultant vector is by the magnitude of the first vector, the magnitude of the velocity is the speed, times the magnitude of the magnetic field, times sine the angle between the two vectors that are in the product here. So that means between the direction of motion and the direction of the magnetic field. That would be the angle theta that is in this expression. Now, obviously, that means that there are some opportunities for this force to vanish to be equal to zero. And that is, of course, if I have a neutral charge. So that means equal number of electrons and protons, or positive and negative charges in some object. So therefore, it doesn't experience any force as it goes through a magnetic field. Or if the particle is stationary, so even if it's charged but it's just sitting there in the magnetic field, it does not experience a force. Obviously, if it's in a region with no magnetic field in the first place, then there will be no magnetic force. And then the last situation, of course, has to do with the angle, because the sine theta itself could be zero when the angle is equal to zero or the angle is equal to pi. And that happens when the particle is either traveling along the same direction as the magnetic field or exactly in the opposite direction of the magnetic field. So the angle theta would be zero if the particle is traveling in this direction, the same as the magnetic field, or the particle is traveling exactly in the opposite direction of the magnetic field, then theta would be 180. And in both cases, there would be no magnetic force. And in the case that the particle is exactly crossing the magnetic field lines in a perpendicular fashion, that would be the maximum of the sine function here, and therefore that would be the maximum angle, or I should say that would be the angle that would give me the maximum magnetic force in this case. The direction of this force can be calculated separately using a right-hand rule. And of course, these right-hand rules are derived based on the rules from the cross product itself, which is a right-handed coordinate system, but there's simplifications of how to find the force, specifically because there's an easy way to specify the roles of the different fingers in this situation. So if I open my palm, so this is an open palm kind of right-hand rule. And with an open palm, the thumb would represent the direction of motion of the particle, the direction of the velocity vector v. The rest of the digits would represent the direction of the magnetic field lines. And of course, the angle then theta between the direction of motion and the direction of the field lines would be represented by that subtended angle between the thumb and the rest of the digits. In which case, the cross product would give me a positive vector that is pointing out of the palm of my hand. So if the charge is a positive charge, that does not change that direction, and therefore the direction of the force would be out of the palm of my